Demonstration problem. A uniform meter stick has a 1 kilogram rock suspended from its left end, as shown below. If it is supported at the 20 centimeter mark, it balances in equilibrium. Since it is uniformly dense, all of its mass appears to be concentrated at the COM, or center of mass, or center of gravity. That would be at the 50 centimeter mark. What is the mass of the meter stick? It is true that the meter stick has mass throughout its length, but since it is uniformly dense, all of that mass appears as if it is concentrated at the geometrical center of the meter stick. That would be at 50 centimeters. Let's look at the force diagram. These are parallel forces, therefore they cannot be concurrent. They cannot intersect at all. Therefore, we cannot assume a point of concurrency and collapse the meter stick to a point at that point of concurrency. Therefore, we look at the forces on the meter stick and we keep the entire meter stick in our force diagram. There are two downward forces. The contact force of the rock, weight of the rock, which is transmitted via this rope that it is suspended from. The weight force is a field force, no contact, exerted from the center of the earth. It acts at the center of mass or center of gravity at the 50 centimeter mark. The support contact force acts upwards at the 20 centimeter mark. We now go through the problem solving process. The givens are that the mass of the rock is 1.0 kilograms. POA, or the point of application of the support force shown here, is at the 20 centimeter mark on the meter stick. The center of mass of the meter stick, since it is uniformly dense, is 50 centimeters. The unknown. What are we looking for? We need to know the mass of the meter stick. The equations. Since the meter stick is balanced, it is in equilibrium. Therefore, the first condition, equilibrium, applies. The sum of the upward forces is equal to the sum of the downward forces in magnitude. And the second condition of equilibrium, or that all the torques are balanced, or that the sum of the clockwise torques is equal to the sum of the counterclockwise torques, also applies, where torque is force times r perpendicular, which is the moment arm of the force. Substituting in, first of all, for the sum of the upward forces is equal to the sum of the downward forces in magnitude. We get the upward forces, we get that the only upward force is the support force, so we write F sub S. On the other side, we see that the downward forces are the weight of the rock and the weight of the meter stick. These forces must be balanced. So we have the force of the supporting member is the weight of the rock plus the weight of the meter stick. The weight of the rock is the mass of the rock times the acceleration of gravity, which we know the mass of the rock is 1 kilogram. We substitute in for that. 1 kilogram times 9.8 meters per second, we get that the weight of the rock is 9.8 newtons. Therefore, we can write that the supporting force is the weight of the rock, or 9.8 newtons, and for the weight of the meter stick, we can write mass times the acceleration of gravity, where the mass is the mass of the meter stick. This is what we want to find. We have one equation and two unknowns here, so we're stuck. We must write the second condition of equilibrium, or that the torques are balanced. To completely solve this problem, we need to find the mass of the meter stick, M, and we would like to find the supporting force, F sub S, shown here. To do that, we need to apply rotational equilibrium, or the second condition of equilibrium. The sum of the clockwise torques is the sum of the counterclockwise torques. Before we can proceed with this equation, we must pick an axis of rotation. Remember that you always pick the axis of rotation at the point of application of an unknown force, so that the unknown force magnitude does not appear in this equation. Since we do not know the supporting force, F sub S, let's put the axis of rotation at the point of application, POA, of the supporting force, or at the 20 centimeter mark. To apply the second condition equation for the torques, we need the moment arm of each of the forces. Consider the weight of the rock force. Its line of action is shown here. The line of action of the force is an indefinite line both ways extending along the force vector. The moment arm is the perpendicular distance from the axis of rotation, depicted here, here, to the line of action of the force. That is this green line shown here. That's the moment arm for the weight of the rock force. We can see that that moment arm is 20 centimeters. The moment arm for FWR is 20 centimeters. Now consider the moment arm for the weight of the meter stick force. The moment arm is a perpendicular distance from the axis of rotation to the line of action of the weight force. That is this magenta line shown here. It has a length of, this is 50 centimeters from the left end to the center of gravity or the middle of the meter stick. This is 20 centimeters. Subtract 20 centimeters from 50 centimeters and you get that the moment arm is 30 centimeters for the weight of the meter stick force. This is shown here. Now we know that the moment arm for the weight of the rock is 20 centimeters and that the moment arm, or R perpendicular, for the weight of the meter stick is 30 centimeters. We're now ready to substitute into this equation that the sum of the clockwise torques is the sum of the counterclockwise torques. The sum of the clockwise torques, imagine a pin driven through the axis of rotation so that the meter stick can only rotate about that pin. We see that the weight force tends to rotate the meter stick in a clockwise direction about this pin. Therefore, the weight force has a clockwise torque. So the sum of the clockwise torques is simply the torque of the weight force, which is the magnitude of the weight force times its moment arm. Weight is mass times the acceleration of gravity. We know that the acceleration of gravity is 9.80 meters per second per second. The unknown that we're trying to find is the mass of the meter stick, so we write M for that. Its moment arm is 30 centimeters, as shown before. For the sum of the counterclockwise torques, the only counterclockwise torque is that exerted by the weight of the rock. So the pin here at the axis of rotation is where the meter stick can rotate, and we see that this weight force tends to rotate about that pin, tends to want to rotate the meter stick in a counterclockwise direction. So we write the force of the rock times the moment arm of the rock, and we have already found that the weight of the rock is 9.8 newtons, 1 kilogram times the acceleration of gravity. Its moment arm is 20 centimeters. We can now algebraically solve for the mass of the meter stick. We get that the mass of the meter stick is 9.8 newtons times 20 centimeters from this side of the equation, divided by the acceleration of gravity, 9.80 meters per second, times 30 centimeters. This gives 2/3 or 0.67 kilograms or 67 grams to two significant figures. Note that we did not have to change centimeters to meters or standard length units because we were not trying to calculate a force. So we have now solved the problem.